In this tutorial we will do Omni robot navigation using Nav2. For robot control we will use ROS2 control. In this project, as a sensor, we are using only a 2D Lidar. This means that both odometry and self-location are calculated based on scan data. This method can be implemented to various robots. In this tutorial, we are using a 2D Lidar to calculate odometry. Let's see how it works. Conversely to traditional approaches, this method does not search for correspondences but performs dense scan alignment based on scan gradients. For every scanned point, the range flow constraint equation is formulated in terms of sensor velocity. Here, small r is scan gradient, large R is range scan where t is time, and alpha is scan coordinate. Motion estimation is obtained by minimizing the function of geometric residual for every obtained point by a LiDAR. The function f is the Cauchy estimator. This function is effective for reducing relevance of the points with very high residuals. This method is applicable to all robots equipped with a 2D LiDAR and moving on a plane. For example, we can use it with Omni wheels, Mecanum wheels, four-wheel steering and crawler. The advantage of this method is that it is much more accurate than usual wheel odometry because it is not affected by wheel slip or floor surface condition. To create a map, we will use Cartographer. Let's see briefly what Cartographer is. Cartographer provides a real-time solution for indoor mapping generating 2D grid maps with a 5 cm resolution. It does not employ a particle filter. To cope with the accumulation of error, it regularly runs a pose optimization. Cartographer combines separate, local and global approaches to 2D SLAM. In local approach, each consecutive scan is matched against a small chunk of the world called submap. This method accumulates error over time. Sparse pose adjustment is used to optimize poses of all scans and submaps. Relative poses where scans are inserted, are stored in memory for use in the loop closing optimization. In this tutorial we are using a robot with 4 Omni wheels. Let's see how to find velocity of each wheel to drive the robot in desired direction. Here we have a robot. Alpha is an angle of the first wheel offset from the x-axis. L is the distance between robot center and the wheel. We want the robot to move in x and y directions and rotate with angular velocity omega. Wheel velocity will be expressed with these 3 values. Component of x directional velocity which contributes to wheel 1 rotation, is shown by the orange arrow. Since it points to the direction opposite to v1, it has negative sign. Similarly, we can find a component of y directional velocity which contributes to wheel 1 rotation. There is also angular velocity component which is represented as a product of robot angular velocity and distance between robot center and wheel center. This formula can be generalized for each wheel in this matrix form. The signs may differ depending on coordinate system, but the method of calculation remains the same. There is also one thing that should be mentioned about Omni wheels. In case of 3 wheels, there are no limitations for wheel velocity because there is no redundant degree of freedom. But in case of 4 wheels, there are wheel velocity combinations when robot might get stuck. This could lead to actuator damage. With usual operation this should not happen, but this is a thing that we should keep in mind. Now we are going to install packages required for the simulation. Firstly, install the ROS2 control package. Then, install the ROS2 controllers package. Install Gazebo. Next, install Gazebo RAWs packages. Gazebo RAWs packages is a set of RAWs packages that provides the necessary interfaces to simulate a robot in Gazebo. It integrates with RAWs using RAWs messages, services and dynamic reconfigure. Install the Gazebo RAWs 2 control package. This package integrates the RAWs 2 controller architecture with the Gazebo simulator. Install the Navigation 2 package. Navigation 2 has a lot of tools such as localization, path planning and path following. It is a successor of the RAWs 1 navigation stack and it has become more flexible and easier to use. Install the Navigation Bring Up package. This package is used to bring up scripts and configurations for the Nav2 stack. Install the Cartographer RAWs package. We will use Cartographer to create a map. Now let's see the code. Download the project from the Google Drive. Before doing the simulation, make sure that you have moved this Omni stage folder into the Models folder under the Gazebo directory. Let's look at the launch file we will use to create a map. Move to the launch directory inside the Gazebo simulation package and open the Cartographer /launch py script. In this chunk we are launching Gazebo. Here, Robot State Publisher is launched. This package allows you to publish state of the robot to TF2. Once state gets published, it is available to all components in the system that also use TF2. In this part we are launching joint controllers. Forward velocity controller is a controller of each Omni wheel, and joint state broadcaster reads all state interfaces and reports them on joint states topic and dynamic joint states topic. Joy node is required to operate the robot using joypad. Here we are converting joypad inputs to velocity commands for each wheel. Here range flow based odometry node is launched. With this setting, this node subscribes to the scan topic and publishes the odom topic with 20 Hz. These are the two nodes related to Cartographer. Let's see these launch files in detail. In the Cartographer launch script we are launching the Cartographer node. The Cartographer node is the SLAM node used for online, real-time SLAM. Also, here we launch the RIS2 node. Our VIS2 is required to check whether the map has been constructed successfully or not. In the Occupancy Grid launch py script, Occupancy Grid node is launched. The Occupancy Grid node listens to submaps published by SLAM, builds a RAWs occupancy grid out of them and publishes it. Now let's create a map. Launch the Cartographer SLAM launch py script. Move the RViz and Gazebo simulator so that you can see both. Drive the robot until the map is created. Do not hit the wall or make fast pivot turns. After the map is created, execute MapSaver CLI to save the map. MapSaver retrieves map data and writes it out to map.pgm and map.yom. Use the F option to provide a different base name for the output files. The map will be saved in the home directory. Also, do not forget to move these files to the Maps folder in Gazebo simulation package before doing navigation simulation. Now, since we have a map, we can do navigation. Before doing the simulation, let's check the parameters file. There are several differences in parameters compared to those used in the differential drive robot. Firstly, in the AMCL settings we should apply Omni motion model. Secondly, because our robot can move in any direction, we should set maximum values for y direction velocity, acceleration, deceleration, and number of samples. Overall, we should set y direction related parameters. Also, do not forget to change username and the parameters path in SDF file and build the project. To start the simulation, execute the Gazebo Sim Launch RF20 script. In the beginning we should give the robot initial position. Use the 2D pose estimate button to do this. If the robot localizes itself successfully, global cost map and local cost map will appear. After this, using the nav2goal function, you can set the goal position for the robot.